Hi everyone, welcome back to Physics 1. We're starting a new chapter today, and we are going to be looking at the same kind of problems that we've been doing, analyzing forces and motion, but we're going to be looking at it from another perspective, and that perspective is energetics. So in this chapter, we're going to be learning what work means, okay? We're going to be defining kinetic energy and looking at some conservation laws of energy and using those relationships to solve problems. So we've been talking about motion basically since we started this class, and we are still going to be talking about objects in motion, but now we're going to be analyzing them from an energetic point of view. And we're going to be looking at objects in motion. And the energy of an object in motion is called its kinetic energy. So this is the energy of objects in motion. And that motion is defined by the object's velocity. Okay. So we're also going to introduce the concept of work and energy and the conservation of energy, which is a law that will help us solve some problems that we've been looking at previously in an easier way. And it's also going to let us solve problems that maybe we didn't have enough information to solve using Newton's laws alone. So let's define what work is. When a force on an object does work, that means that the object is undergoing a displacement. Okay, so in other words, work is the energy transfer by a force on an object, making it move. Okay, so in order to do work on an object, I should say, that object needs to move. So if we have a box or a particle, as we call it, because we always represent our objects as point particles, right, when we draw our free body diagram. So if a box or a particle moves through a displacement S while in constant force is acting on it in that very same direction, then the work done by the force on the particle is simply F times S, okay? The magnitude of the force times the magnitude of the displacement. And so here's a real life example of doing work. So these people are doing work on the car because they're exerting a force on the car and that car is moving. Okay. So the unit of work is the joule. So this is a unit of energy. Okay. This is a unit of energy. Work is a type of energy. And since work is equal to the force times the displacement, the unit of work, joules, is a Newton meter. Okay, so 1 joule is a Newton meter. So to put this in a sentence, if you were to lift an object with a weight of 1 Newton, and you were to lift that object 1 meter at a constant speed, well, then you've done 1 joule of work on that object. So we're going to look at work done by a constant force, okay? And what does constant force also mean? Constant acceleration, right? So we're going to look at work done by forces that are constant. In other words, the acceleration or the change in velocity is constant. In general, we can define the work done by a constant force as Fs cosine theta, where theta is the angle between the force vector and the displacement vector. You may recognize this as being the magnitude of a dot product. Okay, so in other words, the work done on a particle or an object by a constant force moving in a straight line displacement is simply the force vector dotted or scalar product with the displacement vector. So let's kind of put that idea into practice with this example. So using the man pushing a car context, we have Steve exerting a steady force of 210 newtons on a stalled car, and he pushes it a distance of 18 meters. And because the car is a flat tire, he must push the car at an angle of 30 degrees to the direction of motion. How much work does Steve do? So the car here is the object that's moving. So the displacement of the car is going to be along the road in a straight line. And the force that's being applied, it's a pushing force, so it's going to be in the same general direction of the displacement, but it's going to be at an angle of 30 degrees from the displacement. So that's the picture of what we're looking at. And we know that the work is simply the dot product of the displacement and the force, which comes out to be Fs cosine angle between those two vectors. And therefore the work is simply 210 newtons times 18 meters times cosine of the angle between those two vectors. Right, and that comes out to be 3,000, let's say 3,300 joules. 3,300 joules. So that's part A. And then in part B, Steve is pushing another car, but the way that we're given the force and displacement is through vector notation. So the force is 160 newtons I hat minus 40 newtons J hat. The displacement is 14 meters I hat plus 11 meters J hat. And then we're going to dot those two. So remember what the dot product is in that form. It's the x component of each one added to the y component of each one multiplied, right? So we can do that pretty easily. So we're going to multiply the x component of F times the x component of the displacement, add that to the y component of F multiplied by the y component of the displacement. And those get added together. So make sure you put negatives where they are, where they need to be. And that comes out to be 1,800 joules. So you may be wondering, okay, what is this negative energy here? What does this negative 40 mean in the context of work? So let's take a look at that. Positive work is defined as when a component of the force is along the displacement direction. So the dot product, as a result, is positive. You can think back to our definitions of dot product. There was a slide that illustrated this. Back to dot product definitions. Okay, and so what is negative work then? Negative work is when you apply a force that is not in the same direction, or it's anti-parallel to the motion, and the dot product of that would be negative, right? So actually, let me flip over to that slide that I'm talking about here for dot products. There it is right here. So a scalar product can be positive, negative, or zero, right? Depending on the angle between A and B. So we reviewed two cases. Positive, A dot B is positive, or in our case, we're looking at F dot S. It's positive when that angle between A and B is between 0 and 90, okay? Less than 90 degrees. Between 0 and less than 90 degrees. Because when it is equal to 90 degrees, well, then A and B are perpendicular and the dot product is 0. And then if B is, has a component that's pointing anti-parallel to A, in other words, the angle between B and A is somewhere between 90 and 180, then the dot product is negative. Okay, so this is just our dot product relationship. So let me scroll back, right? Remember this? These are two equivalent expressions of the dot product, AB cosine theta and this one right here, right? The x components multiplied together plus the y components multiplied together plus the z components multiplied together. So work is simply a scalar product of the force vector and the displacement vector. Oops, there we go. Right, so no work is done if the force direction is perpendicular to the displacement direction. So in other words, in the case of the car being pushed by Steve, okay, there's other vectors going on, right? We have weight. Gravity is exerting a force on that car, right? But it's pointing straight down, which is perpendicular to the displacement direction, right? So in other words, gravity is doing no work on this car. Let's look at another example of no work. So another reason that no work could be done is if the displacement vector is 0, right? Another way to get this dot product to equal 0 is either theta is 90 or 270, right? Or S is 0 or F is 0. But obviously if there's no force, then what are we talking about? Or the displacement is 0. So we have a weightlifter holding a barbell still, right? The barbell is not moving. Is the weightlifter doing work on the barbell? Technically, no, he's not, right? He's holding it stationary. So there is no motion yet. And therefore, there is no transfer of energy, okay? There is no motion yet. He is just holding it still. And, in your mind, you're like, well, it does take work to hold it up against gravity. But that's not the definition of work that we're talking about here, right? The definition of work that we're talking about is moving an object through a displacement, the energy transfer associated with that. So in this case, he's not doing any work on the barbell at this moment, okay? But let's now look at what happens when he lowers the barbell. So let's analyze the work done in this situation where we have a weightlifter lowering a barbell to the floor. Let's look at it from two different aspects. The first aspect we're going to look at this is focusing on the weightlifter himself or his hands. And we're tracking the hands. We're looking at all the forces on the hands. And the specific force of the barbell on the hands, that force is doing positive work on the hands because the force direction down is in the same direction as the displacement of the hands, which is also down. We can expand this example a little bit if we draw a free body diagram of the weightlifter. So the weight, or the hands really, well, it's all together, right? We're treating him as a singular point object. We have his weight vector, right? All his mass being pulled on by gravity. And then we have also the force of that barbell. Okay, I'm drawing it magnitude is bigger, but it may not be bigger. And we can discuss two different things here, right? We can discuss the work done by the barbell on the hands by examining this, or we can talk about the work done by gravity as he lowers his hands. And the work done by gravity on the weightlifter's hands is also going to be positive because that vector points down in the same directions as the hand's displacement. right? Here we're tracking the hands. This is the hands displacement. So now let's look at a different aspect. Let's compare the work done on the barbell. Okay, so now look, the weightlifter, he's all grayed out. We're looking at the barbell and we're checking the barbell's displacement now. Okay, it's down. And what are the forces acting on the barbell? Well, there's a couple. There's the force due to gravity, right? The barbell's weight times gravity. And then there's the normal force of the hands on the barbell, right? Because there's contact between the hands and the barbell, so therefore there'll be a normal force. And that normal force is the force of the hands on the barbell. And that vector is pointing up. So with that vector pointing up and the barbell moving down, the weightlifter's hands does negative work on the barbell. That's because the force of the weightlifter's hands on the barbell is opposite to the displacement direction. So we need to be really specific about the forces that we're talking about and tracking what is just being displaced, okay? In this case, both the hands and the barbell are being displaced in the same direction and by the same amount. And the only thing that's moving around here is considering the force vector that's acting on those objects. So the total work that's done on an object, it's going to equal the net force on the particle as it moves through that displacement. So in other words, if I have a box sliding, okay, and I have a lot of different forces on that box. Let's say I have a push force. Let's say I have a friction force. Let's say I have gravity. Let's say there is a tension as well, okay, being pulled on it. If we were to add up all those forces and get the net force direction, then the total work being done would be that net force direction dotted with the displacement. Okay, so we can add up all the forces and then do the dot product, or we can do the dot product 4 times and add up all those values. Does that make sense? Either way, you get the total work. And we'll do an example just like that. So let's look at some general statements. If the total work being done on that object is greater than 0, is positive, that means that particle is speeding up. It's speeding up. How did we get to that? Well, because that means that the sum of all the forces, okay, F net, is pointing in the direction of motion, right? And we also know that the sum of all the forces is equal to the mass times the acceleration. So that means the acceleration vector is also pointing in the direction of the motion. And so if your acceleration is pointing in the same direction as your motion, you're speeding up, right? Now let's look at the other case. Well, if the work done is negative, then that particle is slowing down. Well, that makes sense because that means that F net is pointing opposite to the direction of motion. Which means that A is pointing opposite to the direction of motion as well. And therefore, your velocity is decreasing, right? So you're slowing down because your acceleration is pointing opposite to the motion direction. So your velocity is getting slowed down. Okay? So the main idea here, before I move on to the next slide, is that the sign of the work tells you the direction of the sum of all forces on that object. It tells you if the direction is toward the direction of motion or 180 degrees from the direction of motion. And that also tells you that the acceleration direction. Okay? And then you can relate that back to the speed. So let's do this example where we're going to take a look at the work done by a couple of different forces. Some will be negative, some will be zero. And then we'll take a look at the two ways we can find the total work done. So in this situation, we have a farmer driving a tractor and it's attached to a sled loaded with firewood. The sled is pulled a distance of 20 meters along a level ground. The weight of the sled is 14,700 newtons and the tractor exerts a constant force at an angle. There's also a friction force that's opposing the sled. So what do we need to find? The work done by each force on the sled, and then the total work done by all the forces. So let's ask ourselves these questions. What is the object that's moving? That's the sled. Okay, so we're going to draw the free body diagram on the sled. And then what are the forces acting on the object? Well, we have the weight force, right? The force due to gravity. We have the tractor exerting a force, and then we have the friction exerting a force. So our free body diagram will have three forces. Weight, friction, which always acts opposite to the motion direction, and then the tractor's force, which is at an angle from the motion direction, and then S is along this way. So now that we have our three force vectors, let's find the work done by each force. So the work done by the tractor is going to be the force that the tractor exerts on the sled, dotted with the displacement of the sled. So that's going to be a 5,000 Newton force times 20 meters of distance times cosine of the angle between the force vector and the distance, or the displacement vector, and that was 36.9. Okay, and we get something like roughly 80,000 joules. In other words, 80 kilojoules. What about the work done by the weight or gravity? Say work done by gravity. Force of gravity, which is the weight vector, displacement. Well, that's the weight vector's magnitude, mg, times the displacement of 20 meters, and then cosine of 90, right? Because the angle between the weight vector and the displacement vector is 90, so that no work done by the gravity. Now let's check out the frictional force. We have frictional force dotted with the displacement. So that's going to be magnitude frictional force times magnitude of the displacement times the angle, cosine of the angle between them, which is 180 degrees. Right? Because there's the displacement vector and there is the frictional force, 180 degrees difference. So we're going to get a negative sign out of the 180. And then the frictional force, well, that's given to us. If it wasn't given to us, we would use mu k mg to find that. But we would need the coefficient, which we don't have. But they gave us the magnitude of the frictional force is 3,500 newtons, 20 meters displacement, and then cosine of 180. So that is negative 70 kilojoules, 70,000. Okay, so what's the total work done then? All the individual works, tractor, gravity, friction, we get plus 80, plus 0, minus 70. So the total work done is plus 10 kilojoules. Okay, so there's another way we could find that. Instead of doing these three calculations, we could add up the force vectors. We could add the force vectors. There we go. So, so that's one method of finding the total work done. The other method of finding the total work done is taking the net force dotted with the displacement. So let's find the net force. It's the sum of all the forces in the x and the sum of all the forces in the y. Okay, so the net force, let's get all our x components. So we have a positive F tractor, cosine 36.9, right? That's our x component here. And our Fy is here. Just sine 36.9. Okay, so here's our y component. There is no x component of the weight vector, but there is a y for the, there is a y component for the weight vector, which is obviously mg. I believe that's told to us up here. That's 14,700. I'll just leave that as W for now, and we'll plug in all the numbers later. And then finally, the frictional force is in the negative x direction, so that is negative Fk. All right. So the x components added together, we get 5,000 for the tractor's force, cosine 36.9, minus the frictional force, which was 3,500 newtons. So the total, so F net in the x is going to equal 5,000 cosine 36.9 minus 3,500. So that's roughly 500 newtons. I'm rounding here. It's 498.4. I'm going to round to 500. Okay. And now let's do the y components. Move this guy out of the way. He's always in the way. So the y components, we have Ft sine 39, so that's 5,000 newtons, sine 36.9, minus the weight vector, which was 14,700 newtons. So that's going to be our F net y. Put that in the calculator. Make sure you type in sine and not cosine, like I just did. I get negative 11,700 newtons. Okay. So, in other words, the total force is going to be 500 newtons I hat minus 11,700 newtons J hat. My displacement was 20 meters I hat plus 0 meters J hat. Total work can also be expressed as the net force dotted with the displacement. So all I'm doing is this, which comes out to be 10,000 joules, right? This goes away because it's 0 times 11,700. So we get the same answer. Which one's more work or less work? In this case, they seem to be about the same. And what I mean work now is the same amount of time plugging in numbers, doing calculations, right? So they take about the same amount of time to do both methods, but in certain situations, you may find one method more clear than the other. So this goes to show you that you can express the total work done as simply all the forces added together and that force dotted with the displacement, or you can find the work done by each force on the object and then add those up. And sometimes you need to do both, right? Because these are both equivalent. So these are both equivalent statements right here. And you can set them equal to each other. It's just like the definition of a dot product, right? You have the definition of the dot product with the components, and then you have the definition of the dot product with the magnitude. So you can these are equivalent. So in other words, F net dot S is equal to the work done by all the forces added together. Okay. So in the context of this problem, F net dot S is also equal to the work done by the tractor plus the work done by gravity plus the work done by the frictional force. You can set the right-hand sides of both of these equal to each other. Okay? So now let's take a look at kinetic energy and how it relates to work. So we just saw that the total work done on an object by external forces on that object is related to the displacement, right? Force net dot displacement. So if that's related to the displacement, we can also see that it's related to the speed of the object, right? Because if the work done is related to F net, and F net is mass times acceleration, well, then the total work must also be related to the speed of the object, right? Because the acceleration tells you how the speed changes. So let's take a look at that. Let's take a look at the energy of something moving with a speed v. So when a particle or an object is in motion, it has what we call kinetic energy, and that's energy due to its velocity. And the definition of kinetic energy is right here. It's 1/2 times the mass times the speed of the particle squared. So just like work, the kinetic energy of a particle is a scalar, right? It's not a vector. Even though velocity is involved, you can see that it's squared. So we become a vector. We become a scalar. So kinetic energy only depends on the mass and then the speed, right? Not necessarily the direction. So kinetic energy, in other words, can never be negative because everything in there is going to be a positive value, right? Mass is positive, and then the square of anything is positive. So it can be zero, though, when the velocity is zero, right? The SI unit of kinetic energy is also a joule because it's an energy. So a joule is a Newton meter. So you can already see that if the units of work and kinetic energy are the same, they have to be related to one another. So, just kind of elaborate, right? Kinetic energy, it doesn't depend on the direction that the object is moving. It can be moving up, down, left, right. The speed is what matters, and the mass of the object is what matters. So these two objects have the same kinetic energy, even though they're moving in different directions. Kinetic energy increases linearly with mass, right? Obviously. As mass increases, kinetic energy will increase as well. In terms of velocity, well, kinetic energy increases with the square of the speed or the velocity, right? Because of all right, so if we increase v, well, then k is going to be increased by a square, right? So a object with speed 2v will have a kinetic energy of 4 the original value. All right, if that's k prime. well then the new kinetic energy will be 4 times the original because the speed is now increased by a factor of 2. Now let's get to the nitty-gritty, okay? How are force, work, and kinetic energy related? We kind of hit the tip of it a little bit, right? We know that force is mass times acceleration due to Newton's second law. And we can actually express the acceleration in terms of the velocity, right? If we're dealing with constant acceleration, which we are, we can use a kinematic equation to express acceleration in terms of velocity. And so here's that kinematic equation with, instead of v and v naught, we're using v2 and v1, okay? So, and then instead of x minus x naught, we're using s, right? Is this looking familiar, right? That's the third kinematic equation that eliminates time. So if we express the acceleration in terms of velocity squared, we get this expression right here. And we solve for acceleration, all right? We plug that in to Newton's second law, right? This is acceleration. And once we plug in the acceleration into Newton's second law, well, we can find the definition of work as force times displacement. So now we multiply that by displacement, which gets rid of this s in the denominator. And then we can clean up time, right? Distribute the m to each term. And when you do that, you get a 1/2 mv squared here, and you get a 1/2 mv squared here. So in other words, kinetic energy at velocity 2, kinetic energy at velocity 1. In other words, that's the change in kinetic energy. So the total work done, Fs, is also equal to the change in kinetic energy. That's the work energy theorem. And we derived it by simply using kinematic equations at constant acceleration. Right? Plugging it into Newton's second law right there. So it's not really horrible. Go through it, a few times. I kind of just talked you through it, but it's really going to connect the dots when you do those substitutions and you do the algebra yourself. So we have 2 ways to define the total work, right? The total work is the sum of all the forces on that object dotted with the displacement of that object. The total work is also equal to the change in kinetic energy. The final kinetic energy minus the initial kinetic energy. Or, the energy at some point 2 minus the energy at some point 1. So we have two definitions now for total work. So let's look at a problem where we utilize the work energy theorem. We can take a look at an example that we did a little bit ago, and we can see that we can find the speed of the sled after it's moved 20 meters. All right, this is the sled that is attached to the tractor. So if we are told that the initial velocity of the sled attached to the tractor is 2 meters per second, and then once it's moved 20 meters, after the result of all those forces acting on it, the friction, the tractor, the weight, we can actually find the speed of the sled after it's moved. So we know that the total work done, if we look back at example 6.2, it was 10,000 kilojoules, or 10,000 joules, in other words, 10 kilojoules, right? And what we just saw, how did we achieve that? We found the sum of all the forces, dotted it with the S, the displacement, right? That was our answer, plus 10 kilojoules. Well, we also know now that the work Total work done is equal to the change in kinetic energy. So change in kinetic energy, this delta is always final minus initial. So the final kinetic energy, which was what we're solving for, minus the initial kinetic energy using V1. So that would be 1/2 m V1 squared. We're going to need the mass of that sled, right, to solve for V1. So we were told that the weight vector was 14,700 newtons. And we know that that's equal to mass times gravity. So the mass is going to be equal to 14,700 newtons divided by 9.8. 1,500 kilograms. So we know M is 1,500 kilograms. Let's finish setting up this equation, right? This work done calculated in this fashion is exactly the same as work calculated in this fashion. So we can set those two values equal to each other. 10 kilojoules equals final kinetic energy minus 1/2 mv1 squared. Well, what is the final kinetic energy? That's 1/2 mv2 squared. We can plug in our values. And then solve for V2. Should have done this on another page. Oh well. So let's add 1/2 1,500 2 squared. Okay, then we're going to multiply by 2, divide by 1,500. And we get, make sure you follow the order of operations, 10 plus 0.5 times 1,500 times 4 divided by 1,500 times 2, 4 meters per second, roughly. Okay, so not too crazy, right? It's not too crazy. It actually, it's kind of easy. What's the hard part here, right? Conceptually, things got a little bit easier, but the hard part is going to come from reading the problem and assigning, you know, the correct values to the correct variables, right? So let's take a look here at this example and do just that. It's reading comprehension, right? The bigger the question, the more reading comprehension is required. So we have a 200 kilogram steel hammerhead of a pile driver, okay? So this gold piece here, okay? Big object that we're gonna assume is a point particle. And it begins at a point 3 meters above the top of an I-beam, okay? So above the thing it's gonna hit. When the hammerhead is dropped, it drives this I-beam, okay, 7.4 centimeters down into the ground. The vertical guide rails exert a constant 60 newtons of friction force on the hammerhead. Okay, so this force of 60 newtons is acting on the hammerhead. Use the work energy theorem to find the speed of the hammerhead just as it hits the I-beam and the average force that the hammerhead exerts on the I-beam. Exert any effects of air, such as air resistance. So in the picture, right, the object is gold, right? So we're going to be drawing a free body diagram on this hammerhead thing. So let me use black. So free body diagram, hammerhead. I'm going to call it HH, okay? We got the weight, of course. And then we have friction, right? The vertical guide rails exert a constant 60 newtons of friction force on the hammerhead. And you're looking at this picture like, what the heck is it talking about? Okay? It doesn't matter, right? How does friction act on something? It acts in the opposite direction to the motion. We definitely know which way the hammerhead is going. It's going straight down, right? Hence the green arrow. So friction, vertical guide rails, blah, 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 what the heck, doesn't matter. It's going opposite to the direction of motion. So friction will be pointing up, okay? And what other forces are acting on it? That's about it. That's about it. So we're going to use the work energy theorem to find the speed of the hammerhead just before it hits the I-beam. So what does the work energy theorem state? I'll write it up here. Okay, the acronym is a little unfortunate here. So work energy theorem is that the total work done is equal to the change in kinetic energy. And we know another way to calculate the total work done, right? We know that the total work done is also equal to the sum of all the forces on that object dotted with the displacement of that object. So we're going to set this side equal to this side, right? Because these two are equal. So let's go ahead and do that. Let's figure out what Fnet.S is, all right? So Fnet, there's two forces there. Let's add them together. They're both in the Y. Okay, we're doing components here. It's going to be equal to the frictional force, positive, minus the weight. So that is going to be, were we told the weight of, 200 kilograms. So the weight is 200 kilograms times gravity, and then the frictional force is 60, right? So we're going to get 60 newtons minus 200 kilograms times 9.8, right? This is the sum of all the forces in the Y. So this is Fnet Y. So let's put that in the calculator. 60 minus 200 times 9.8, negative 1900 newtons, okay? The net force direction is pointing down. Does that make sense? Yes. Why? Because that heavy hammerhead thing is pointing straight down. It's falling down. Its purpose is to go down. So then some of all the forces on it should be pointing down, right? So we have our Fnet. Now let's find the total work done using the first definition that we learned, which was kind of the second one. Fnet dot displacement. So we have negative 1900 newtons. I'll go ahead and write this in vector notation. J hat dotted with, so this thing is going straight down. If we are going to put our XY coordinate system like this, okay, we should actually put it, okay, so look, if we do it like this, where our 0 is at the bottom, then our displacement vector will be down, right? Our S vector will be down. And our force vector will also be pointing down. So we should end up with a positive answer, right? So in order to get a positive answer, we need to make sure our displacement vector is negative as well because it's pointing down, and we defined our coordinate system to be up as positive. So I'm going to put in a negative, how far is it going? 3 meters, right, for the hammerhead. J hat. So let's do the dot product here. Well, it's just two numbers multiplied together because the angle between them is 0, right? 0 degrees between F and S here. So it's 1900 times 3, 5,700 joules. and it's positive, and that makes sense, right? Because it's moving in the same direction as the net force is going. So the total work done is 5,700 joules. So now let's apply the work energy theorem, which states that 5,700 joules should be equal to the change in kinetic energy. So that should be equal to the final kinetic energy minus the initial kinetic energy. So what do we want to know? We want to know the speed of the hammerhead just as it hits the I-beam. So we want to know the final kinetic energy, right? Its final position, just before it hits the I-beam, just before it gets stopped. What's the initial kinetic energy? So this is one of those unspoken givens, right? The initial kinetic energy, we're taking it at this resting point, right? Before we have set it in motion. So the initial kinetic energy is going to be 0 because the initial velocity is 0. So it's another one of those hidden or implied conditions. So in other words, simply equal to the final kinetic energy because Ki is 0. So kinetic energy is defined as 1/2 mv squared. We'll go ahead and call that V final. All we got to do is solve for V now. So we do that. We get VF equals, I'm going to do a bunch of algebra, 2 times 5,700 joules over the mass, and then square root of that. So the mass was 200 kilograms, right? So we got 2 times 5,700 divided by 200, and then square root that. We get 7.54 meters per second. So that's how fast that the pile driver is going to be moving right before it hits it's, the thing it's supposed to be hit, the steel I-beam. So let's tackle part B of this example. We are looking for the average force that the hammerhead exerts on the I-beam using the work energy theorem. So the average force that the hammerhead exerts on the I-beam, well, that's cluing us in to take a look at either the hammerhead or the I-beam when they're in contact. So let's then draw the free body diagram of the hammerhead while it's in contact with the I-beam. And we can actually do either one because some of the forces on there are going to be an action-reaction pair with the other. So I think it's just best to start with the hammerhead. So when the hammerhead is in contact with the I-beam, well, the hammerhead is going to have its weight vector, of course, and it's going to have some frictional force as well. And then the final force that it is experiencing is due to the contact between the hammerhead and the I-beam. And so that's going to be the normal force, right? The normal force is the force that the surface exerts on the object. In this case, the surface is the I-beam and the object is the hammerhead because this is the free body diagram of the hammerhead. So these are all the forces acting on the hammerhead while it's in contact with the I-beam. And the work energy theorem tells us that the total work done will equal the sum of all the forces acting on that object and that move that object along a displacement. And so when the hammerhead is in contact with the I-beam, it's moving a very small amount, but it is moving, right? It's moving 7.4 centimeters, driving that I-beam down into the ground. So this will be the, sum of all the forces on the hammerhead while in contact with the I-beam. And then this is going to be the hammerhead's movement while in contact with the I-beam. So let's add up all the forces now, except we have an additional one since the hammerhead is in contact with the surface, so we have the normal force. So let's get our F net. Everything is in the Y. So we have the normal force is positive. We have the frictional force as positive. And then we have the weight. So let's add up all these force vectors. We don't really know N. We know the friction, that was 60. And then the weight is 200 kilograms times 9.8. So this is the net force in the Y. We know that the total work done is equal to the net force times the displacement. So the displacement now is going to be 7.4 centimeters downward. All right. So we are going to get our F net as N, let's see, plus 60 minus, this is 1900 newtons, right? So that becomes N minus 1900 newtons. And the J hat dotted with negative 7.4 centimeters, so 0.074 meters, also in the J hat. Okay, it's pointing down. We're driving that I-beam down, and the net force direction should also be down. So why? Because in order to drive the I-beam down, we need that hammerhead to be also moving down. So let's leave it like this, okay? Let's not multiply it out yet. So let's find the work done the other way, right? Using the work energy theorem. Change kinetic energy. Final kinetic energy minus initial kinetic energy. So the final kinetic energy in this situation is when the hammerhead and the I-beam are at its lowest point, right, where they have stopped. So this is going to be 0 because hammerhead and I-beam are at rest. And then this is going to be the final kinetic energy from part A. Why is that? Because this is the initial velocity of this situation. The I-beam and the pile driver moving down together 7.4 centimeters, right? So when they first meet, the pile driver, the hammerhead or whatever it is moving at 7.54 meters per second, because that's what problem A asked us to solve, right? Find the speed just before or just as it hits the I-beam. So that's going to be 7.54 meters per second. So this is 0. So our total work done using the work energy theorem is going to be negative 1/2 m 7.54 meters per second squared. Oops, there we go. And let's get a value for that. 200 kilograms. We get negative 5,685 joules. Okay, so we found the work done by using the change in kinetic energy, and we got a value. And we have an expression for the work done using the force times the displacement. So let's set them equal to each other and find N. So negative 5,685 joules will equal the normal force minus 1900 newtons in the j hat dotted with negative 0.74 meters in the j hat. So now when we, well, what we can do is the j dot j goes away, right? J dot j is 1. So this is just an algebraic multiplication of two numbers. Okay. And so what we can do is we can divide by negative 0.74. So that's why I didn't want to distribute it yet, because I knew it would be going away. And then add 1900. So 5,685 divided by 0.74 plus 1900 will give me my normal force. Which is quite large, basically 7,800 or 78,700 newtons. So let's take another look at kinetic energy and kind of see if we can draw a stronger meaning from kinetic energy. So in order to accelerate a particle of mass m from rest to some speed, the total work done on it must equal the change in kinetic energy. So the total work done must equal 1/2 mv squared. So what you can think of the kinetic energy as, you can think of it as the energy required to accelerate it from rest to its present speed, which is equal to the work done. The last example we'll do in this video lecture, it's kind of a conceptual one. So let's consider two ice boats, and they are in a race, but one is twice as heavy as the other. They're sailing on, a frictionless surface as well. The wind is exerting the same constant force on each ice boat, and they start from rest, crossing the finish line a distance s away. Which ice boat crosses the finish line with a greater kinetic energy? So we can use the work energy theorem to answer this question, which has the greater kinetic energy. And I know initially what you want to do. I already know what you want to do. You want to do this. You want to do k equals 1/2 mv squared, and then k2 equals 1/2 2mv squared. And you want to tell me that the second boat will have more kinetic energy, right? But that's assuming that the velocities are the same, and they won't be, right? Because if the same force is acting on these boats and one boat is heavier, then one is going to move slower than the other, right? So you cannot do it this way, because you can't assume that the velocities are equal. But if you take a look at the work energy theorem, which states that the total work done on each boat is equal to its change in kinetic energy. Well, if they both start off with no kinetic energy, and then they end with F dot S total work done, then they end with the same kinetic energy. Why? F is the same for both. S is the same for both. And therefore, the kinetic energy must be the same for both. So what changes, right? Obviously, not every single aspect of these boats are the same. What's the same is that the force is the same, the distance is the same, but the velocity is not. So let's figure out now instead which boat crosses the finish line with the greatest velocity. So if K is the same for both boats, let's call one K and K prime. 1/2 mv squared equals 1/2 2m v prime squared. Let's find the relationship between v prime and v. So we know that k over k prime is going to equal 1. Let's divide the other two. 1/2 mv squared over 1/2 times 2mv prime squared. The 1/2s go away, the m's go away, and I'm left with 1/2 v over v prime squared. So the velocities then, if I move this over here to where the 1 is, I see that I have v prime squared equals 1/2 v squared. Square root both sides, v prime is equal to 1/4 of v. So the second boat, the heavier boat, is going to reach the finish line with 1/4 speed of the first boat, okay? Their kinetic energies will be the same. The forces exerted on them are the same according to the problem. They travel the same distance, but the speed at the finish line will be slower for the heavier boat. So think about this example. This is a conceptual example, okay? This is a very good, a very good exam problem can be drawn from this example. So understand conceptually what is going on with this example. Very important. And that'll end this video lecture for the beginning part of Chapter 6, Introduction to Work and Kinetic Energy.